will give you a little bit more and then information, and then we summarize the whole thing. And today is I'm going to give you more quantitative calculations in terms of memory, the membrane analysis method. Okay, and this one, okay, you see. So the common equations is this, D and on the other side this is the shaft. One is shaft, one is the membrane. So here you can see we compare that, it really is one-to-one mapping. So here the zeta is the diffractions. And so for example, if this is the H and the membrane is under pressure, okay? So this is the diffraction, okay, and P is the pressure, and S is the surface tension in membrane. And for here, the G, the beta, the G is rigidity, US, beta is the angle of the twist per length per L. So right now in this way we can put the analogy is this. The first one, the zeta corresponding is for the phi, and phi is for the stress functions. And partial zeta, partial x, partial zeta, partial y. Corresponding is partial phi, partial x, partial phi, partial y. Okay, and this one basically is minus tau yz. This one is tau xz. So from here, this is for the first time I give you the information. The derivative of the stress function is related to the shear stress. Shear stress is related to the gradient of the diffraction. Two times volume, V is the volume. So basically here, the under diffraction, this is the volume V. QV equal to zeta dx dy, and we take the integral on the base area. This one is equivalent to is 2 times phi dx dy. And this quantity can be shown to equal to torque. So in this way, for your learning, is the torque can be analog to 2 times of the volume under the membrane. And P over S is equivalent to 2G beta So furthermore, we can say P, we can let P is equivalent to beta, and S making is equivalent to 1 over 2G. So I will keep this table, and then we can do a little bit exercise.
Is that S or is that the...
S, yeah, this is S.
No, not that one. The one with the surface
This one.
integral.
This is theta. Theta. So for this exercise, is we consider twisting a rectangular shaft, and like this. The length is equal to L, and it has the base dimension H, and the other one is B. And in this way, let me give the coordinate systems. This is Z, and this is X, and this is Y. Okay. So to this problems, the interest is to find the tau maximum. Okay, and again, for this case, you can see this is a shaft, and then say here we give the torque is in these orientations about Z. So from last time, we can exercise is this. You can see this is the cross sections of the cross-sectional sections of this shaft, and these dimensions is B. This one, H. Okay, so at this moment, before we proceed, I need you to identify where is the maximum shear stress. Look at this cross section.
At the
Top and bottom?
center of the
A, B, C, D. A
A,
and C. The top and the bottom center here. So that the maximum will be here and here. Okay. So that is using the information last time we talked about, and basically you could imagine is this, and you can try to imagine this will be the membrane and that be forced by the pressure that is pushing from behind the wall, pushing up. Okay, and then that can be diffraction and making the contours of the diffraction will be something like this. And from here you can see the contour distribution of the contour is denser in this direction than in this direction. So that means the maximum occurs here. Okay. Again, looking at this table, and the stress is related to the gradient. So using this information, we can identify. And then this is a more qualitative. And in this example, I want to show you is more quantitative. And that way we can try is this. So looking at this one as a membrane, And that is from the top view. And now I want to look at it from the side view. So from the side view, will be like this. So this is the support of the membrane. This is the support of the membrane. So this is the reference line. Okay, the membrane will be pushing off, deflected due to pressure. The pressure is from underneath. And the diffraction will be something like this. Due to the aspect ratio of the membrane base, the diffraction of the membrane will be more flat toward the center than compared to the two sides in this view. On the other side, we'll look at it from different viewpoint. So that diffraction from this view will be like this. Okay. The coordinate systems, this is Z and this is Y, and this is Z and this is X direction. Okay, so now I will apply the tables and to do something about this one. The first one is this, let us look at these regions. In these regions, this region basically is far away from the boundary's influence. Okay, in this way you can see that it's pretty much flat. That's saying that it's pretty much flat. That means the diffraction respect to Y is pretty much flat. That means the gradient variation is pretty much small, 0. Okay. And again, this one can be very accurate if we assuming the aspect that is a very thin, very long rectangles. If that rectangle have a similar dimension, then this one won't work, because due to the boundary condition, the influence. Okay. So therefore, because this one is equal to 0, so the governing equations of this one, the membrane becomes like this. Minus P over S. So that means from the governing equation, we can drop the second term on the from the left-hand side. So we have this one. So therefore, from here, we can solve for this equation pretty much quickly. And that one, epsilon will be the function, zeta will be the function of x. And that one can be equal to minus P over S2, 2S, and x squared plus C1x plus C2. And here the C1 and C2 are the boundary conditions, and here is this. This one is the boundary conditions determined by the boundary condition. Boundary condition is this. We know that the zeta at look at here. At this point, and at this point, the diffraction equal to 0. So we're using that two boundary condition to solve for the function of the x, C1, C2. So from here, we can get that one is, therefore this one will be equal to P over 2S and H squared over 4 minus X squared. Okay, and then here, then if we have this one, then we can calculate the volume. V is the volume and V is the volume. That means the volume underneath of the diffraction. Let me label this one. So volume basically is equal to zeta and do the integration over the area. So that one, we can plug in this one, do this one quickly, and that one can be shown equal to P over S times BH cubed 12. We got all the information on the analogy on the left-hand side, and we are trying to map into the shaft on the right-hand side.
That's 2S, not 25, right? Just making sure.
Yeah.
This is where 2S side. How to best write this one? 2S.
It's a curse back.
I'm fine with that.
Okay, so now with this one, then I'm trying. So for this case, we try to map all the information to the right column here. And the sequence of the mapping is basically arbitrary. Okay, and then I just follow my lecture notes. And how about let me use the color. V basically is equivalent to, you look at that one, V is equivalent to T over 2. Okay, and P over S is equivalent to 2G beta. So we plug in here, T over 2 equal to 2G beta times 12 BH cubed. So therefore we can rearrange T equal to G beta BH cubed divided by 3. Okay, and usually the people like to define the symbol. So if we define this one as the J basically is kind of the polar moment of inertia. Okay, J is the rho. You can treat this J as the polar moment of inertia. And so this one basically can be defined as the G beta J. Okay, so let me highlight this one. And think about this one. You can see this equation. We know that from here, let me do the kind of scratch calculation. G times beta by definition is the angle of the twist divided by L and times J. You can see in this way, B will be equal to TL over GJ. And that is the equation you memorize in the fundamental torsional shaft, right? So basically here we're doing the things like this one. And the J plate for the circular shaft, we know the J is pi over 2 times radius to the fourth power. And you can see this is to the fourth power of the dimension. So basically they have the same role here. Okay, so that is the first one we obtained. And so this is about the torque, and then we can try to get the stress. Force stress.